Hey everybody, it's Thursday, April 8th, and as you can see here in the aim today, our goal for today's video is all about how we can apply concepts associated with energy conservation to the horizontal block oscillator systems that we've been discussing over the last few days. Now, yesterday, we really introduced the idea of how we could apply energy to looking at these systems. And so that's really where I want to pick back up. I'm sure you remember at the end of yesterday's video, the last thing we did was we took a look at a problem. Now, really what I wanted to do was take a look at two problems. The video was getting a little long, so I figured I would just show you the one. Now I want to take a look here at the second one. This problem says a 0.25 kilogram mass at the end of a spring oscillates 2.2 times per second with an amplitude of 0.15 meters. Determine the speed when it passes the equilibrium point, the speed when it's 0.10 meters from the equilibrium, C, the total energy of the system, and D, the equation describing the motion of the mass. Now, there are a lot of things that we can say about this problem, but I think the first thing that you should recognize here is all of the equations that we derived yesterday for the maximum speed, which would be the square root of k over m times a, or the speed in general, which was v equals the square root of k over m times a squared minus x squared. Those equations require you to have the spring constant. And as you probably noticed, we don't have the spring constant. And so the first thing we're going to do here in this problem is we're going to go ahead and solve for the spring constant. Now, it should be noted based on some of the other little tips and tricks and that little pattern recognition thing I tried to show yesterday, there are actually some other ways you could go about answering this without having the spring constant. But since those equations aren't in the reference table, I think you should definitely be familiar with taking a more standardized approach. And so the first thing we're going to do here is, I guess, what we'll call like a part zero, which would be to solve for the spring constant K. And so in order to solve for the spring constant K, we're going to need a couple of pieces of information. If you take a look at the frequency equation for a spring block oscillator, you'll see that the equation is 1 over 2 pi times k over m. And so if we're solving for k, we need the mass and we need the frequency. And they give us the mass and they give us the frequency. It's important to realize frequency is a measurement of cycles per second. So when they say 2.2 times per second that this thing is oscillating, that is a measurement of the frequency. And so here we'll say in our knowns then that the frequency is 2.2 cycles per second, or in other words, hertz. And we'll say here that the mass is 1/4 of a kilogram because, well, it is. And so we take that frequency equation that's written in the reference table, or actually it's not written in the reference table, the period equation is, but you can get it from the period equation. You just flip everything around. We have frequency as 1 over 2 pi times root k over m. So I'm going to go through showing like how to manipulate the equation. You're all good at math. I'm sure you all know this, but just to be clear, this one is a little annoying. Your first move should be to move the 2 pi f over to the other side. And so we have 2 pi f equals the square root of k over m. Then, of course, we're going to want to square both sides. And so we're going to get 4 pi squared f squared, right? 4, of course, because 2 squared is 4. And then that's going to be equal to k over m. And then we're just going to multiply that k over to the other side. And so that's going to give us k equals 4 pi squared f squared m. And that's the equation we're going to plug into to determine the spring constant. So we have 4, that's a constant, pi squared, that's a constant, and then we're going to plug in the frequency squared, so we have 2.2 hertz, and then we're going to square that, and then we have here the mass, 0.25 kilograms. And when you do that math, plugging in all those numbers, making sure you have everything in the right spot, you solve for the spring constant, and you get a value of 47.7689. And of course, that's measured in units of newtons per meter. And then we're going to round that off to, let's call it 2 digits because these two numbers are given to 2 significant figures. And we'll go ahead and we'll call that 48 newtons per meter. There's our spring constant. And so now we're just about ready to be able to do part A. Because part A of this question, let's just go back and remember, part A was asking what is the speed when the thing passes the equilibrium point? What you need to recognize is the speed when the object passes the equilibrium point is its maximum speed. That is the location where all of the elastic potential energy is converted to kinetic energy. And so the speed when it passes the equilibrium point is the maximum speed because that's where the object has the maximum kinetic energy. So for part A here, to determine this speed, we need the spring constant, which we just found as 48 newtons per meter. We need the mass of the object, which is 0.25 kilograms. And we need the amplitude, which if you missed it, because we didn't really go too nuts about noting it in the beginning, the amplitude was given as 15 centimeters or 0.15 meters. We're looking for Vmax. So as we derived yesterday, Vmax is equal to the square root of K over M times A. Now, this is an equation that I do think is helpful to memorize, but you do not have to memorize it. If you just remember that the total energy at this point is equal to the kinetic energy, and so that means 1/2 Ka squared is equal to 1/2 mv squared, then you just go through and solve for V, and that's what you get. At any rate, that's the equation. We go ahead and we plug into it. We have Vmax equals the square root of K over M, so that's going to be 48, that's parentheses, newtons per meter, 48 newtons per meter over the mass, which is 1/4 of a kilogram. And then we're going to close up that square root, and we're going to multiply that by the amplitude, which is 0.15 meters. And so when you do that math, plugging in all those numbers, making sure you have everything in the right spot, you end up getting a maximum speed of 2.1 meters per second. And that is it for part A. Now to answer part B and all the remaining parts, I'm going to jump over to a different slide. So you may want to pause the video here and write that down. And when you hit play, we'll move on. Okay, moving on to part B then. Part B says here, determine the speed when the object is 0.10 meters from the equilibrium position. Now, this is the question that I'm really interested in answering because we did not get the opportunity to use this equation yesterday. As we saw, when we take the equation, the total energy is equal to elastic plus kinetic, and we say that the total energy is 1/2 Ka squared. That's equal to the potential energy 1/2 Kx squared plus the kinetic 1/2 mv squared. And we solve that for V, we get this equation right here. If you are unsure of what I'm talking about, then go back to yesterday's video because the whole thing is shown. That equation we did not get the chance to use, and so I'd like to take a moment to use it. Now, if we go through here and use the information we're given in the problem, then we can solve for the speed at any location. In this particular instance, they are asking us for the speed when the distance from the equilibrium position, which notice is x, is 10 centimeters. Remember, the amplitude was 15 centimeters or 0.15 meters, so it's no longer going to be at its maximum speed. That's a thing you should keep in mind as we go through this calculation, because if we get a number that's bigger than the maximum speed, we got a problem. And I'm just writing down all the other information here that we're going to end up using in this calculation. We need the spring constant and the mass, and of course, we are looking for the speed. And so, as I discussed, the equation that we derived yesterday that allows us to determine the speed at any location is the square root of K over M times A squared minus X squared. An important thing to mention about this is that a lot of people generally think that the square root of A squared minus X squared is equal to A minus X, and that is not true. Pick a number for A. Pick a number for X. It's not true. Let's take A is 5 and X is 4. If we say A is 5 and X is 4, then 5 squared is 25, 4 squared is 16, and 25 minus 16 would be 9. But 5 minus 4 is 1. And I hope everybody is with me. 9 is not 1. So that is not true. The reason why I am writing the equation like this is because that is how the equation has to be written. It cannot really be simplified in any nicer way than this. It is a little ugly, but that's just what you'll have to deal with. So we're ready now to plug into this thing. We have all the information. So we take our K, 48 newtons per meter. We're going to divide that by the mass of this object here, which is 1/4 of a kilogram. And then we're going to multiply that by the difference between A squared and X squared. And so I'm going to always, when I do this, set up a double parentheses here, 0.15 meters squared minus 0.10 meters squared, and then close up the parentheses. And then I'm going to close up that square root. Now, obviously, you should know how to use a calculator by now. I know that you all do. But this is an easy one to make a mistake with in the calculator. What I like to do is I take 0.15 and I square it. Then I hit answer minus and I do 0.10 meters squared and I get that number. then I multiply by 48, I divide by 0.25, and then I take the square root. There's no reason to be a hero and try to put this all in your calculator in one move. You're going to end up needing like a million parentheses. It ends up being a little bit of a nightmare. In a lot of cases, I advocate doing it all at once. In this instance, I think maybe it's not the smartest idea in the world. And so if you want to follow along with me right now and do it, maybe that would be a smart idea. So I'm going to take 0.15 and I'm going to square that. And I get 0.225. Then I'm just hitting the minus sign. Now it says answer minus, and I'm doing double parentheses, 0.10, close parentheses, squared, close parentheses again. That gives me 0.0125. That's everything here in these parentheses for a squared minus x squared. Now I'm going to multiply by 48. That gives me 0.6. Then I'm going to divide by 0.25. That's essentially multiplying by 4. And so that's going to give me 2.4. Then I'm going to hit answer for the square root button. So I'm hitting second x squared on my calculator. I have a TI that's allowing me to do the square root button. Then I'm hitting second and minus sign, which is pulling up the answer. And that gives me a speed of 1.54919, whatever. So I'll write 1.549. It ends up being 193338, whatever. That doesn't matter. We're rounding this to 2 digits anyway, and this is all we need for that. We're going to end up calling this 1.5 meters per second. Now, when I see that number in my calculator, 1.5 meters per second, I'm breathing a sigh of relief because that number is less than what I said my maximum speed was, which was 2.1. And so that makes a pretty good amount of sense, I think. A lot of people, when there is a square root, forget to take the square root. This one is really going to hurt my feelings if you do that. Because if you forget to take the square root and you calculate that the speed is bigger than the maximum speed, then that really makes no sense. This is the speed at 0.1 meters from the equilibrium position, and it's going to get smaller and smaller as it moves away from the equilibrium position where the speed is a maximum. Now, looking back at the question, just in case you forgot what it was asking, part C is asking you for the total energy here. And there are actually a bunch of different ways that you can do that. I'm going to go ahead and just calculate both of them, I guess, because why not? And so I think considering that we're working with kinetic energy so far, and we might as well just stick with that. I'm going to say that the total energy here is just going to be 1/2 m v max squared. Notice I'm not writing down the knowns again because I've already written every single one that I need for this multiple times now. So I have 1/2 of the mass, which is 1/4 of a kilogram. And I'm going to multiply that by the maximum speed squared. Remember, the maximum speed was 2.1 meters per second. And I'm going to square that whole thing. And that gives me a total energy of 0.55 joules to 2 digits. So that's my total energy, a little over half a joule. What I think is important to realize also, though, is that you could find the total energy by using the equation 1/2 Ka squared. This 1/2 mv max squared represents the maximum kinetic energy. But the kinetic energy is converted from the potential energy that the spring had when the person pulled the spring back and gave it an amplitude. And so this equation should work as well. And notice it does. If we take 1/2 48 newtons per meter, that's our K, and we multiply it by the amplitude, 0.15 meters, and we square that whole thing to 2 significant digits. Once you do that math, you end up getting 0.54 joules. Now, some of you might be looking at that and saying, wait a second, it's different. Yeah, but not really. I think it's important to realize this number, 2.1 meters per second, was rounded. This number, 48, was rounded. Don't go nuts about it. It's not that big of a deal. They're off by a little bit. There is no circumstance where you would do this on the AP test and get marked wrong. It's off by 0.01 joules, an amount that is so small you would barely be able to measure it. Don't go nuts. Those are, as far as we are concerned, the same answer. To answer part D, we're going to go on to another slide. So take a second to pause this video here and write that down. And when you hit play, we'll move on to part D. Now, I like part D. Part D is a nice review question. It talks about something that we were talking about before the break, and I think it's probably a good thing to bring up again. It says here for part D, write down the equation describing the motion of the mass. Assuming that at t equals 0, x was a maximum. What does that mean? All right, so they want us to describe the motion of the mass here, assuming that x was a maximum. Assuming that x was a maximum effectively means the position versus time graph is going to look like this. And that means this thing is going to start out as a cosine. Now, sometimes they're going to say, assuming x was a minimum, in which case you'd need to modify the template that's shown to you in the AP reference table. But remember, the template in the AP reference table says the position function is going to be given by x equals a times the cosine of 2 pi f times t. They already told us that x is a maximum, so we're going to leave it as a cosine. If they told us it was a minimum, we just change the cosine to a sine. So the amplitude here is 0.15 meters. We're going to multiply that by cosine, and then we have 2 pi. Remember, our frequency here was 2.2 hertz, and then we're going to multiply that by t. Now, obviously, that is disgusting looking, and so we want to fix that up a little bit, and so we'll keep this as 0.15 meters out front, and then we'll multiply that by the cosine, and of course, 2 pi times 2.2 is going to be some silly number, but we can at least say 2.2 times 2 is 4.4, and so we can say cosine of 4.4 pi t, and there's our function. If we went to our graphing calculator and punched that in, it would show everything about the object's motion. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now that's really it for the calculation portion of the energy discussion for simple harmonic motion. The only other thing I want to do here is answer conceptual questions. If you go to the post on Google Classroom for today, you will see a worksheet attached to this post. And the first problem I want to talk about on this worksheet is the first problem that's listed on the first side of that worksheet, which is in the Tipper's book. It's B7QRT13. This question says, the title is Displacement Time Graph Energy Quantities. It says a cart attached to a spring is displaced from equilibrium and then released. A graph of displacement as a function of time for the cart is shown. There is no friction. Points are labeled A through H in the graph. And they ask a series of questions. There are a bunch of different parts to this. I want to go through them one by one. The first part, part A, says at which point or points are the spring potential energy and the cart's kinetic energy both at their maximum values? This is a question you should be able to answer on your own, and I actually want you to do all of the questions on this worksheet on your own and sort of follow me as I go through this. So take a second to pause this video here and try to figure this out. At which point or points are the spring potential energy and the cart's kinetic energy both at their maximum values? Put an answer, put an explanation, and when you've got both of those, hit play and we'll go over it. All right, for part A here, they're asking about where the potential energy and the kinetic energy are both at their maximum values. And in my view here, the answer is pretty straightforward. The elastic potential energy and the kinetic energy transfer back and forth. One turns into the other, turns into the other, turns into the other. And that means that one is at a maximum when the other is at a minimum. This means they cannot simultaneously be at their maximum value. When one is maximum, the other is minimum, and vice versa. Take a second to pause this video here and write this down, adding any parts of this explanation that may be missing from your own. And when you hit play, we'll move on. All right, moving on to part B here. Part B says at which point or points is the kinetic energy equal to 0? Give it a shot. What I think is important, and I'm just going to say this once here before you do this question, is it is really important to think about the elastic potential energy being a really important part of this whole thing. The elastic potential energy is determined by the position of the object, and the kinetic energy ultimately is determined by the elastic potential energy. Because the elastic potential energy is going to be whatever it is, depending on where the object is located. And the kinetic energy is going to be whatever it has to be, such that when it is added to the potential energy, it keeps the total energy of the system constant. So let's just say the total energy is 4 joules. The way you essentially figure out what the kinetic energy is you say, well, what's the potential energy here? Because whatever is left over is kinetic energy. So I want you to keep that in mind as you answer this part and the next few parts. So go ahead and kind of come up with an answer, come up with an explanation. And when you got both of those, hit play and we'll go over it. All right, for this one, it's pretty straightforward, I think. The kinetic energy is going to be 0 where the velocity is 0. The velocity and the kinetic energy are 0 where the elastic potential energy is maximized. And so the kinetic energy is 0 here at the maximum displacement from the equilibrium position, or the amplitude, as this is the location where all the kinetic energy is converted to elastic potential energy. That means at points A and E, well, those are the points where there's 0 kinetic energy. It's really important to be able to make sense of this, I think. Yeah, you can say, well, the slope of the velocity versus time graph is 0 there since kinetic energy is proportional. to the speed, that means the speed being zero means the kinetic energy is zero, sure. But I think it's really important to understand this in terms of energy. According to the equation, potential energy equals 1/2 kx squared. The elastic potential energy is maximized when the displacement is maximized. And that means that the kinetic energy has to be at its minimum value at that point. Now, the minimum value for both of these types of energies happens to be exactly zero, and so it's zero. Take a second to pause this video here, write that down, add to any parts of this explanation that may be missing from your own, and when you hit play, we'll move on. All right, moving on to part C here. Part C says at which point or points is the total energy at its maximum value? Take a second to pause this video, try to come up with an answer, come up with an explanation, and when you think you've got both, hit play, and we'll go over it. All right, this one I think is kind of a dirty little trick. It's a super easy question. All you need to know about the total energy in an oscillator like this is that it's conserved. The total energy is conserved in this system. So the total energy is always at the same value, which is its maximum value. The total energy is at its maximum value at literally every single point. Now, you could list A, B, C, D, E, F, G, and H, but you could just write all. That's fine. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, moving on to part D here. Part D is asking at which point or points is the spring potential energy negative? Explain your reasoning. Pick an answer, come up with an explanation. When you think you've got it, hit play, and we'll go over it. Again, this one is another one of these dirty little tricks. I think what they're trying to make you think is that the energy is going to be negative when the displacement is negative. Now, first of all, you could say, well, the displacement in the spring equation is squared. So even when you square a negative displacement, it's going to end up giving you a positive number. But I wouldn't even get that far. Period, end of story, energy is a scalar. So it never has a negative value. The elastic potential energy is at a negative value at none of these points. Kinetic energy and elastic potential energy are never, ever, 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 ever negative. Is that clear enough? Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. When you hit play, we'll move on. All right, moving on. Next question, part E asks, in a kind of similar way, at which point or points is the kinetic energy positive? Come up with an answer, come up with an explanation, and when you think you've got both, hit play, and we'll go over it. All right, now I think this one represents a basic kind of a trick as well, because what I think they're trying to get you to say is, oh, well, we just said for the last question, energy is never negative, so the answer here is all of them. That's not true. As we've said, sometimes the kinetic energy is zero, specifically at the amplitudes at point A and E. And so if you wrote all of them for this one, technically you're wrong. What I wrote here is the kinetic energy is a scalar. So wherever the kinetic energy has a non-zero value, it'll be positive. As previously established, the kinetic energy is only zero at the amplitudes, points A and E. So it's positive at all the other points. Kinetic energy is positive at B, C, D, F, G, and H. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. When you hit play, we'll move on. All right, next part here, part F, says at which point or points is the kinetic energy at its maximum value and the spring potential energy at its minimum value. Take a second to pause this video here, come up with an answer, come up with an explanation, and when you hit play, we'll go over it. Again, I think it's really important when you're thinking about these questions to really consider the kinetic energy as being a function of the position, because the elastic potential energy is a function of the position. Look at what I wrote. I wrote here the kinetic energy is converted from elastic potential energy, which is a function of the position. So the kinetic energy is essentially a function of the position. Since the elastic potential energy is directly proportional to the displacement from the equilibrium position, at the equilibrium position, the system has zero elastic potential energy and thus has its maximum kinetic energy. The kinetic energy is at its maximum value at points C and G, as those are the points where the elastic potential energy is zero. That's the idea. Basically, the kinetic energy is going to be whatever it has to be, such that when you add it to the potential energy, it gives you the value of the total energy of the system. It is converted from the elastic potential energy. The elastic potential energy is a function of the displacement, And the kinetic energy is just going to be whatever it has to be to ensure that energy is conserved. Take a second to pause this video here and write this down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. Okay, moving on. Last question on here, part G. At which point or points is the kinetic energy at its minimum value and the spring potential energy at its maximum value? Take a second to try to answer this question, come up with an answer, come up with an explanation. When you think you've got it, hit play, and we'll go over it. All right, so this answer is basically exactly the same as the last one. Kinetic energy is converted from the elastic potential energy, which is a function of the position. So the kinetic energy is just a function of the position too. Since the elastic potential energy is directly proportional to the displacement from the equilibrium position at the amplitudes, the system has all elastic potential energy and no kinetic energy. The elastic potential energy is at its maximum value at points A and E, as those are the points where the elastic potential energy is maximized and the kinetic energy is zero. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. When you hit play, we'll move on. Okay, so I want to, before we move on to the other questions on this sheet, just take a moment to think about another question. This part is the humor part, part H. At which point or points is the kinetic energy equal to the elastic potential energy? This is a nice little question. I want you to think about it. Based on everything I said so far, you should be able to figure it out. Take a second to pause this video and just think. We're going to write this down, but I want you to just take a second to think. And when you hit play, we'll go over it. Sometimes in physics, you get a counterintuitive answer, right? Like let's think about the acceleration due to gravity. Heavier object? Come on, gravity's pulling on it more. That's why it's heavier, right? So surely it's going to have a larger acceleration than a lighter object. Nope, forgot about the inertia. The inertia means it's going to end up having the same gravitational acceleration. Here, you really got to resist your intuition, because your intuition tells us it's got to be at the halfway point, right? Halfway point is where it's going to be half the energy is one kind and half the energy is another kind? No? The answer is no. The key to understanding this is that the elastic potential energy is not directly proportional to the displacement. It's directly proportional to the displacement squared. This is a big important point here. Common sense dictates that at the halfway point, the energy split between the potential energy and the kinetic energy is half and half. Since the elastic potential energy is directly proportional to the square of the distance, though, at the halfway position, which is the half the amplitude, the elastic potential energy is only a quarter of what it once was at the amplitude, meaning the elastic potential energy is only a quarter of its original value. And I guess I'll write here at the amplitude. And so that means the other 3/4 of the energy is kinetic energy. This is a really important point. If you think about it, I think it does make a pretty good amount of sense. Let's go back to that other picture. I am going to put this back up in a second, but I want to go back to the other picture here for a second. Let's say this is the amplitude. When the object is at the amplitude, meaning the spring is stretched all through this distance all the way to here, that's where the spring is exerting the largest force on the object. As that spring continues to speed up the object, the force the spring exerts on the object is going to get smaller and smaller and smaller and smaller. And the reason why, of course, is because the spring force is directly proportional to the displacement. What that means is the object does most of the speeding up here in the beginning. Look at how curved it is. This is where it's accelerating the most. As it continues to go from the amplitude toward the equilibrium position, notice the slope is getting steeper and steeper and steeper, but it's not changing as much. Here, it changes really fast between A and B, but then not so much between B and C. And that's the idea. The object's speed is changing the most at that very beginning. Notice, by the time it gets a quarter of the way from the amplitude to the equilibrium position, it's already gained a heck of a lot of speed. By the time it gets halfway, already 3/4 of the energy is kinetic energy. And so the point here is that because the elastic potential energy is directly proportional to x squared, if you really want to determine the displacement, which produces a 50-50 split between the energies, you got to use the 1-1-1 rule. And so the way I see it is it makes a lot of sense to look at it like this. The elastic potential energy maximum is equal to 1/2 Ka squared. I think it makes a lot of sense then to solve this for A. You get 2 US over K square root, right? And so that means we can also write an equation here. Notice this equation would be US max. We can also write an equation for X that says this is going to be 2 US not max over K. And so if we want to figure out where the energy is going to be half of the maximum, well, then all we have to do is plug that in, X prime, and then we'll plug in here 2 times 1/2 of US max over K. And so notice what we have here is not 1/2 the distance, but the 1/2 under the radical. And so we're going to have X prime equals the square root of 1/2 times 2 times US max over K. And notice, because we said the square root of 2 times US max over K is the amplitude, what we have here is X prime equals 1 over root 2 times the amplitude, or 0.707 times the amplitude. Right, 1 over root 2 should be a number that's fairly familiar to you from math. And so that's the idea. By the time it reaches the halfway point, already 3/4 of the total energy is kinetic energy. It only has to go, according to this, about 30% of the way from the amplitude. Let me just go back to this picture. It only has to go about 30% of the way to 0.707 times the amplitude until the energy is 50-50. That's going to be not quite at point B, because notice point B is 0.75, right? The amplitude, because it's 3 out of 4 total. So it's going to be like right there, just a little over. Not 0.75, but 0.707. And so I'd like you to take a second to pause this video here and write that down, because this thing is very important. The energy doesn't change half and half when the distance is half and half. You have to be very careful when you're doing the 1-1-1 rule when there are radicals involved. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now just to really kind of put a pin in this idea that the energy changes in a way that is a little confusing because of the x squared in the equation, I want to take a look at the second problem on this sheet. This is the last one we're going to do. I know there's a third one, but we're going to skip that because it's kind of silly. But this problem is a nice problem, I think. B7 BCT14, oscillating mass on the spring displacement time graph energy. It says here, a card attached to the spring is given an initial push, displacing it from its equilibrium position. A graph of displacement as a function of time for the card is shown at the right. The system has an initial energy of 12 joules, and there is no friction. 5 points are labeled A through E in the graph. A, B, C, D, E, you can see them up there. And it says here, for each labeled point, complete the bar chart below for the kinetic energy and the potential energy for the cart spring system. Now I'm going to go here and just change my ink color to red. I kind of want to just talk about this for a little bit. I really just want you to watch and think. So look at point C. What do you notice about point C on the graph? Point C on the graph is the equilibrium position. Notice here, they have filled in kinetic energy for the equilibrium position. So all we have to do to finish out point C is ask, well, how much potential energy does this thing have at point C? And because potential energy is directly proportional to the displacement from the equilibrium position, and that is the equilibrium position, the energy here is 0 for the spring energy. That means point C was actually already finished for us here. It told us here, too, that the system had a total energy of 12 joules. And if you notice, this chart has this bar going up to the 1, 2, 3, 4th line. So that means each line can be determined from the height of this bar. That line is 12 joules. The pen really doesn't work on these images, so I apologize for that. That one's 9, then 6, and then 3, right? So each bar is 3 ticks. Now, the first thing you should be thinking of, because it says complete the bar chart below for the kinetic energy and the potential energy for the cart spring system, the first thing you should be thinking about is, well, what can I do first that's just easy? Let's look at points A and E. Points A and E or at the amplitudes. What should you be able to say about this system at the amplitudes? Well, at the amplitudes, K, the kinetic energy, is 0. That means E total is just equal to the potential energy there. So that means if we just make bars that are the same height as the other one, 4 ticks high, if you will, and color them in. This pen really doesn't work on these images. I apologize. But that's the basic idea. We've now filled out 2 points in one shot here because all the energy at the amplitudes is potential energy. It stops there, so it has no kinetic energy. So that's it. Now we only have to fill in points B and D. Now, if you look at points B and D, here's the point that I was trying to make earlier. That's the halfway point. It seems like a lot of people might think it's going to be 2 bars and 2 bars, kinetic energy and spring potential energy. That is not true. At the halfway point, at x equals 1/2 a, you can look and say US maximum equals 1/2 Ka squared. And so that means the spring potential, US prime, is going to be 1/2 times K. And notice that distance is half the amplitude. And then we got to square that. That means the spring energy there is going to be 1/2 squared, or 1/4, 1/2 Ka squared, which means it's going to be 1/4 times the US max. That's the deal. At half the displacement, the potential energy is 1/4 because it's proportional to x squared. And because the total energy is 4 bars, that means this is pretty easy. At point B, this is just going to be 1 bar for the potential, 1, 2, 3 bars for the kinetic. And that's really it. Notice here, in a rather simple way, we've shown that we understand with this chart the relationship between the spring energy and the displacement, and how conservation of energy applies to the situation in all cases. Because notice, in every case, if you add the height of the 2 bars, keeping in mind at A and E, the height of the bars is 0 for kinetic energy, and at C, the height of the bar for the spring energy is 0, then the sum of the heights of both bars is just 4 tick marks. And that's really it. Take a second to pause this video here and fill this chart out. This is going to be very important when it comes time for the test. And when you hit play, we'll move on. Now, I want to write a note about this. You can write this as the explain your reasoning on this worksheet, or you can write it in your book if you want. It doesn't really matter to me. The total energy in a spring block oscillator is conserved and always cycles back and forth between kinetic energy and elastic potential energy. The elastic potential energy is proportional to the square of the distance from the equilibrium position, and the kinetic energy will always make up the portion of the total energy that isn't elastic potential energy. You use the displacement information to figure out how much potential energy you have, and then you use how much potential energy you have compared to the maximum amount to figure out how much of the leftover energy is kinetic. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, and that is pretty much it for the energy analysis for a simple harmonic oscillator. The only other thing to say is, in exactly the same way that we talked about motion graphs for a simple harmonic oscillator. So notice this one is described by a sign for the position. And so the velocity is a cosine, the acceleration is a negative sign. It's all about the slope of the tangent here, right? Slope of the tangent starts positive, so the velocity starts positive. That starts at 0, so this starts at 0, etc. So you can just go to any part and boom, figure it out. Here, slope is negative, so the velocity is negative. Here, the slope of this graph is negative, so the acceleration is a little below the x-axis, so that's negative, and so on and so forth. They're all related. Notice here we see the exact same thing, except now the position is starting out as a cosine. In exactly the same way that we show these graphs for position, velocity, and acceleration, we could take a look at these kind of graphs for energy too. I like this graph. It really shows you the relationships. It says you got the total energy shown by this black bar up here, and that's showing you that the total energy is constant. And this graph is really just showing you how the energy cycles back and forth between potential and kinetic energy. And while I do think this is a useful graph, and it's interesting, it shows us the energy in terms of the period. Notice it says there uppercase T, so that's the period. So when it says 1.0 here, that's 1 full period. And notice the energy cycles back from potential, or sorry, that's kinetic energy, kinetic to potential to kinetic to potential to kinetic potential, all in 1 period. A more useful representation of this graph is probably not going to be in terms of the time, but rather in terms of the distance or the position. So notice here, this is an energy versus position graph, and here the position is 0. And notice it says in parentheses there, A for amplitude. That means this is negative A, and this is positive A. And so notice at the amplitudes, the kinetic energy here, shown by this orange bar, drops down to 0 at the amplitudes. It's maximum at the equilibrium position. And here we see the potential energy, 0 at the amplitudes and maximum. 0 at the equilibrium position and maximum at the amplitudes. Notice here, where they both have this 50-50 split, we're just at a little over 0.7 of the amplitude, because that happens at 1 over root 2, or 0.707 of the amplitude. This graph is really important. Take a second to pause this video and write this graph down, sketch it, make sure you really highlight these values, and when you hit play, we'll move on. Now, I'm sure what I'm about to say has been applicable to like literally every other topic we've done for the entire year, but perhaps for this one more than any other, it's probably kind of hard to understand what's going on here without being able to really see how this thing is working in real life. And I found a pretty good simulator online that I think sort of represents how all of this stuff works for an oscillating dynamic system. And so I want to take a second to show you that now. So as you can see, the spring is originally stretched 4 meters. These are just dummy numbers that they put in there. I'm going to put the link in the Edmodo post. You got a mass of the block here of 20 kilograms and a spring constant of 100. And so you run the simulator, and this is going super slow so we can speed it up, and it traces out the graphs here in real time. Super important to pay attention to. I'd like to make this go slow again, reset it, and talk about some of the interesting patterns here. Now first, this thing starts at its maximum positive displacement. So it should not be much of a surprise to anybody when we set this thing going, what this position versus time graph is going to look like. And so I'm going to go back over here, I'm going to hit run. It's starting at its maximum displacement, and so sure enough, we totally would expect this graph to be a cosine. It's starting at the maximum positive position, so the graph is a positive cosine. Now let's see what's happening to that slope of the tangent line. The slope of the tangent line here is 0, then it goes negative, then 0, then positive. And sure enough, that's exactly what we see for the velocity graph. The velocity starts at 0, because the slope is 0, then it goes negative, that's negative, then the slope goes to 0 again, so the velocity is 0, and so on and so forth, and this will always go throughout the whole time. Same thing for the acceleration. Slope there starts negative, so the acceleration starts negative, and on and on. What I like about this one is it also shows you what happens to the elastic potential energy and the kinetic energy, and I'm going to reset this just so we can watch those things evolve in real time. So as you can see, the object is starting at its maximum amplitude. Let me just reset that one more time. It's starting at its maximum amplitude down here. And so, of course, the potential energy starts at its maximum and the kinetic energy starts at its minimum. Then they simply slosh back and forth, continually switching. When it's at the amplitudes, you have max potential. And when it's at the equilibrium position, shown by this middle white arrow here, you have maximum kinetic energy. That's the key idea. Notice once again, because the initial spring stretch is 4, that if I pause this, and we'll see how good I could do, one frame off. If we start at this 3/4 mark, which this scale is slightly off, I don't think it was intended to be to scale, but at 3/4 of the amplitude, or I guess we could say 1/4 of the way back to the equilibrium position, again, is where you get that 50-50 split. It's not at the exact halfway point. Notice at the exact halfway point, if we continue to run it, probably about right. We have about 3/4 kinetic energy, now shown by the green, and 1/4 elastic potential energy, shown by the orange. Now, these pie charts, as you can tell, are not perfect. I guess that's probably the best spot. So notice we're at the halfway point. We have 3/4, 1/4 split. I really think you're able to understand this a little more if you play around with it and you get a feel for it. And of course, what I like about this one too is you can plug in any of the values, solve for any of the quantities, and it shows you how all of these things oscillate in time. And that brings us to the very last thing we need to talk about for the spring block oscillator, which is a phenomenon known as damping. We might as well just get right into it. There's no reason to belabor the point. I think it's pretty straightforward. Damping of a simple harmonic oscillator is a process that occurs as a result of frictional forces acting on a simple harmonic oscillator. And so the question that we really need to ask before we take a look at the definition is, how do you think friction will ultimately affect the motion of a simple harmonic oscillator? There are a lot of ways that we can approach this question. But I think the most obvious approach, considering we're talking about this in the energy problem solving video, is by thinking about energy. If the system loses energy, ultimately the question is, how would you be able to tell? I think the answer is pretty straightforward here. The energy of a simple harmonic oscillator, as we looked at quite a bit over the last few days, the total energy is given generally by the equation 1/2 Ka squared. And if the energy is decreasing because there's friction, then the amplitude is going to decrease. Damping is a physical phenomenon known as the decrease in amplitude of an oscillator produced by the frictional force acting on a simple harmonic oscillator. When friction acts on a simple harmonic oscillator, it is referred to as a damping effect. And that effect manifests itself in a decrease in the amplitude of the oscillator. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I think this really makes sense because friction always does work to convert mechanical energy to heat. And so essentially all we're saying here is that it makes sense that the amplitude of the oscillation would decrease because friction converts some of the system's energy to heat. So there'll be less kinetic energy. That makes sense. The speed is going to get lower. There's going to be less elastic potential energy too. And since the elastic potential energy really determines ultimately what the amplitude is, because it determines what the displacement from the equilibrium position is, if there's less elastic potential energy, then there's going to be less displacement from the equilibrium position. That makes sense. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Let's take a look at how this works. And we're going to take a look at how this works by making use of a pretty good simulator. So as you can see here, I've got this mass attached to the spring, and I turned gravity all the way down to 0 because, again, we're usually going to consider this on a horizontal oscillator, and so we won't go too nuts about the fact that gravity matters. Notice when I do work on this and I stretch the spring, you see there that the energy in the system increases. Right now I have the damping set to 0. I've got this just covering the red line. And so this thing is going to oscillate back and forth, and I'll put it in normal speed, and you can see it's going back and forth and back and forth and back and forth, and the energy is oscillating and changing between kinetic and potential, kinetic potential, kinetic potential, and it always, though, is keeping the total amount of energy the same. Notice when I switch it back to slow, you can see the energy is slowly cycling between elastic and kinetic, but it's always making it back down to that red line. That's because the total energy in the system is remaining the same. Now what I'm going to do is I'm going to turn on the damping, and we can watch what happens. When we put on a little bit of damping here, as you'll see, the total energy starts to turn from mechanical to thermal. And notice as this happens, it stops being able to make it down to that amplitude. It's getting smaller and smaller. Its farthest point from the equilibrium position is now closer and closer to the equilibrium line. That's an important thing to realize. Notice that's the farthest down it makes because the energy is turning more and more into thermal energy or heat. That's the basic idea here. Damping turns mechanical energy into heat, and as a result, the amplitude decreases. Now, an important question that we should probably ask is, how does the damping of a simple harmonic oscillator affect its period? I want you to take a second to think about that. How does damping, the decrease in the amplitude due to these frictional forces, affect the period? Well, it doesn't. Since the period is unaffected by amplitude in general, the fact that the amplitude happens to be decreasing now means the period is not going to change because it's not affected by the amplitude anyway. This actually makes sense if you really dig into it and think about it. Yes, it is true that the object now does not have as much distance to travel back and forth. But because it's losing energy, it's also not going as fast. So yes, there is less distance to travel, but it's also traveling that distance at a slower speed. Notice this is very similar to the exact argument we made about why the amplitude doesn't affect the period in the first place. That's very important for you to understand. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, the last thing we need to talk about in this video is this graph. This is a graph that shows a damped oscillator, as it's called. And I just want to mark up this graph a little bit. Notice here, as this oscillator is damped, the amplitude starts to decrease and decrease and decrease. And notice here, it's decreasing exponentially. This function here happens to be called an envelope function. And it really is just showing you the general trend in the amplitude. You don't necessarily need to know that, but what we see here is that the amplitude is decreasing. What's also important to notice here, though, is that the period remains constant over time. It doesn't get any longer. It doesn't get any shorter. The period stays the same. This is a characteristic graph for a damped oscillator. It shows the period staying the same over time, but it shows the amplitude decreasing over that same time period. With that, that is it for the spring block oscillator. Ladies and gentlemen, we have one more video to go. We are so close to being done with the course. That's it for today. Tomorrow, I'll see you for the last video. Have a good one, everybody.